Hi, I'm Matt Venn, and I've been recently working with Efabless to help boost the number of people able to tape out on the Google-sponsored shuttle. One of the things I've been wanting to do for a while is to put together a walkthrough video that covers the entire process of installing the tools all the way through to submitting your design. This video is about half an hour long, and it's been split up into a lot of different sections covering all the different parts. You can skip directly to the part that you're interested in, and I'll be signposting resources along the way. I've also taken the opportunity to add a custom test bench because your design really should be tested before you tape out to silicon. So having said that, let's get started. The first step is to go to the repository. This is called Caravelle User Project, and we're going to need to follow the instructions here. So we're starting off by creating a new repository. Back to the instructions. Create the directory and change into it. And now we're cloning the repository, and the tag's now changed to MPW-6C, so make sure you change that. Run some git commands that allow us to later push our design to our own custom repository. And you may need to set up your Git credentials. I'm using the SSH one, and my credentials are already loaded into GitHub. I'm choosing the branch to be called walkthrough, and now I can push the repository to my repository. And after that's done, I should be able to go to my repository, reload it, and now it's full of all the information that we got from the one that we just cloned from Efabless. Now we need to set up some environment variables. I'm setting this up in my temp directory, but you shouldn't do that because otherwise when you reboot your computer, you'll lose everything. So put it somewhere where you can keep it safe. And ignore this mistake now. It's not Openlane PDK, it's PDK root. It's very important to get the environment variables correct. That's a common cause of problems, and you can see it's easy to get wrong. And I should say that you're going to need Python and Docker already installed on your system, and those are listed in the quick start guide. And then we run make setup. It's very quick now. I've sped this up 3 times, but it only takes about 1.5 minutes now that we're downloading the pre-built PDK instead of building the PDK on our local machine. If you do want to build the PDK on your local machine, that is still possible, but the recommendation now is to go with the pre-built one because it's so much quicker. Okay, that's done with the install. We're set up now, ready to do a test. And we're going to use Openlane to harden the example project. And this is a good way to check that everything is working. User project example is the example demo project that comes with Caravelle User Project. And this is going to put Openlane to the test and check that we get valid output. So I'll sped this up 5 times. We're in the routing stage now. See those violations dropping down. When they get to 0, we'll move on to the next step. If you want to find out more about how Openlane works, then you can check the links in the description for the Openlane documentation. Now we're building the GDS and doing the DRC. That stands for Design Rule Check, and that basically checks that the GDS file that we've produced is manufacturable by Skywater, the foundry that has given us the PDK. So that is now finished, and we've got some antenna violations which we can ignore, but the important thing is there's no hold or setup violations or DRC violations or LVS violations. So let's take a look at the output files. I'm just finding them all and then counting them. So I've got 314 files. Let's have a look at the tree structure. Lots and lots of files here. Again, check the documentation of Openlane if you want to learn more. And the files that we're interested in are in a folder called Final. Let's just find all the GDS files. And you can see the final one here is the one I want to look, so I'm going to load it with K-Layout. You would also need to install K-Layout if you want to use it. I quite like it. I quite like being able to see this list of standard cells. I'm going to turn off all the fill and decoupling capacitor cells. And you can see the example project is actually a very small amount of logic required, just this little pyramid shape at the bottom. So the actual size of the area of the macro that we've just hardened is much bigger than it needs to be. Okay, so let's move on to adding a custom project. Let's check the structure of Caravel. And we've got DV, that's for the tests, GL for gate list, include files, and RTL. And that's where the project's going to go. So we'll move into RTL. And I'm going to use a very simple project. First, let's remove the example project. I'm going to use a simple project that I developed for my course called 7 segment seconds. And this basically just counts up in seconds on a 7 segment display. So here's my simple design. That's the input and output ports. I'm going to change this max count to 100, so it only takes 100 clocks to move on to the next segment, just in the order to keep simulation fast. And here's where the old example project was instantiated, so I'm going to instantiate my custom project here. I'm going to take these power pins and copy them across to my module. It's not strictly necessary, but it helps with the power routing and helps with the LVS, so I do recommend you do it. And I'm just taking the first digital domain pins here. I don't need any of the others. Okay, so now let's continue with adapting this. So my pins are called clock and reset. I'm not doing anything with the wishbone, so I'm going to delete all of that. Same with the logic analyzer, but I do want to use the outputs. So mine are called LED out. And you're advised to skip the first 8 pins of the output because they're dual use. So I'm starting at pin 8, And IO-OEB is output enabled bar, so bar means low, and they have to be driven low if we want the outputs to be enabled. So I'm going to add an extra port onto my module so that I can drive them all low. And the reason that I'm doing this in my module is because it's harder to put logic or registers or anything that is going to synthesize into a standard cell inside User Project Wrapper. It's best to keep it just wires and modules. Then we need to adapt the includes. So again, remove User Project Example and replace it for your project. And now we're going to add a test. So we already have a bunch of tests here. We can adapt the IO ports test. It's worth reading through these to understand how they work. Forgot the -R to copy the directory. And I'm going to rename the files. It's important that the file names have the same name structure as the directory, because the makefile template is assuming that's the case. You can check these templates out to see how the makefiles work. This is the C firmware that runs on the RISC-V processor that sets up the IOs. So here I'm setting up the IOs to all be outputs for my LED segments. I only need 7. And that bit at the bottom is just waiting for the transfer to be complete. And that's pretty much all I need. Now here's the test bench file. Let's change all these names. A common problem is forgetting this one, and then you load in some missing firmware, and then your design never starts up. The RISC-V never sets the IO ports up, and that can be confusing. I'll show you how that looks in the simulation in a minute. This is a convenience wire, so I can attach it just to the LED segments. That's the clock. That's where we're going to be running the test and dumping the output. Here's the test itself, waiting for those things to be true. Here's bringing up the power domains in order. And here's Caravelle instantiated with a flash interface, and the flash goes to this model that loads our custom firmware. So let's try running this test. Not expecting it to work because we haven't adjusted the actual test, but we should get some traces. And one thing to note is that when you run this make, it's going to fetch a Docker that includes all the tools you need to run simulation. So this test failed, which is not surprising. We've got a VCD file here, so let's take a look at that. Maybe not all 45,000. Let's just take these ones at the bottom. Okay, so if we zoom out, we see the clock start. The power domains come up, those 4 on the bottom. We see the reset taking a bit longer time, and then we see the RISC-V processor starting to read firmware out of the flash, and then at the end we see some results. So we've got those 38 pins from the ASIC, and then we've got the 7 pins from this useful little wire bus that I can now do some tests on. It's just for convenience to make the tests simpler and easier to write. So let's update the test now. And instead of waiting for these things to happen, I'm going to wait for each set of segments to be correct. And essentially the way this test is structured is that it waits a certain amount of time for these things to happen, and if they don't happen within a certain number of cycles, the test fails. So I'm just going to do a bit of VI magic here, where I'm recording a macro, and then I can record, and then I can repeat that macro and repeat it. Made some little mistake there. Yeah, searching for 7, and we've got 7 twice in that line. Fix that up. So now it's going to wait for the display to show the numbers 1 in turn, and then that should finish. So let's run the test again. And we get a pass. So while we're here, let's commit the work we've done that's working, because we don't want to lose this. And also, if you ever get stuck and you want to ask for help, the first question that I'll be asking on the Slack is, can you post me a link to your repository that's up to date with your files? And you want everything up to date in there so that we can easily see what's going on and how to help you. So I'm going to add my new design, the firmware and the test bench. Use a project wrapper where we instantiated the new design. Give it a message. And then push it to our repository. So now I can refresh this page and see it's all up to date. So that shows the Git stuff is all working nicely. And I can look at this diff and see the things that I changed to get my custom project in and the test working. So the next step is to now harden our design. We've got the Verilog, we've got the hardware description language, but we don't have the configuration for Openlane. So we're going to again copy user project example. And I'm going to edit the config file. See if you can spot my mistake. Changing the clock and the net. I'll leave it at 10, so that's 100 megahertz. And I'm going to change the size to be a lot smaller. And I'm also going to change the density, because I know that the way it was, it's not going to work because I tried it before. And to understand that kind of stuff, you just need to practice, play around with settings, explore the designs, see what happens. So that failed because I made a mistake in that config. Did you spot it? Wrong name. So let's edit that. Config again. Fix that up. And try again. So if you get stuck with anything to do with Openlane and the hardening process, then we have an Openlane channel on the Skywater Slack, and there's a link to join the Slack in the video description. If you get stuck with anything to do with Caravelle, that's the kind of the harness that holds the design that User Project Wrapper is part of, then we have a Caravelle channel in the Skywater Slack. And I've sped this up, but it doesn't take very long. There we go, onto the DRC, finished. No DRC, no LVS, no antenna, no hold or setup violations, everything looks good. Took 1 minute and 30 seconds, extremely simple design though. Let's take a look at the GDS like we did before. So, tall and thin, you can still see there's lots of empty space in there. Not going to spend too much time looking at it. And you can see in the GDS, def and the left directories, on a successful run, the files get copied to the right places. So let's add them all. Add the files that we used for hardening. Let's take that pin order as well. Add the GDS, add the def, and add the lef. Good. So, last step in the hardening process is now we need to take that module that we just hardened, that macro, and place it inside the user project wrapper, and then re-harden the user project wrapper. And that is the actual bit that we submit to Efabless. So we need to change some names here. See if I can spell it correctly this time. There we go. If you're putting multiple macros in, you would need to specify multiple extra lefs and extra GDS files. Change the name for the macro hooks for the power distribution network. Update any clock stuff. We need to also change the name of the macro. So instead, before it was called MPRG, and now it's 7 segment seconds. And now let's make the user project wrapper. I've increased the speed again. And because the design is so simple, it finishes very quickly. One minute and 12 seconds, and again, no DRC, no LVS, no setup or hold. I don't know really what those messages mean, but it's not true, at least in most cases I've seen. So let's take a look at the final GDS. And we can see we've got our little new project in there now. The PDN is broken around it, as it should be. The vertical lines, but the horizontal lines continue over to drop down power. So let's commit the work in progress. Now, if your GDS gets big, then you should do a make compress, which will compress all big files. And the reason we do that is because GitHub has a limit on the maximum size of the file. So I'm just adding the GDS files as they are. But if you get warnings about things being too big, then you can do make compress and then add the compressed files. Okay, so let's check this. We've done this part. We've done the hardening, we've done a simulation, we've run some checks. So now we've got on to the last step, which is running the pre-check. So before we can run it, we need to install it. So you do that by running make precheck. And then we can do make run precheck, but I've just remembered we need to update the README. It can't stay the same as it was, or the precheck will fail. So here you should really document your project, write about it. Having good documentation is a really good idea and helps people find out about your project. And now let's run it. The pre-check checks quite a few different things. The most important things is that it fits properly inside the area, that your GDS is good, that there's no DRCs, and the DRCs are checked with both Magic and K-Layout. And we've got a success, everything's ready. Make sure the repo is up to date and push it. All looks good. And the final part is to submit to Efabless. So the website should be updated. That top hand corner now should take you directly to start a new MPW-6 project. You need a title, summary, and the Git URL for your project. And you've got to have .git at the end of it. And then we can save. Then we need to synchronize the Efabless site by doing a git pull. Sometimes takes a moment, depending on when you do this. As we normally get up to the tape-out deadline, things can take longer as Efabless get under more pressure. But here we go, everything is synchronized pretty quickly today. The earlier you get your project in, the better. So don't delay, commit today. Okay, we've got to run the pre-checked on Efabless website. And this currently takes about 5 minutes. You can see the job in there, we can read the logs. Because we've run the pre-check locally, everything should be fine. But you can't run a tape-out job until you have a successful pre-check job. So now we've got our succeeded job, we've got our logs, we've got the time it's taken, about 5 minutes. And we've got the logs out here with the pass at the end, so that's great. And one other thing that's worth checking is you can see the latest commit and the branch name. So sometimes it's worth checking that everything's been synchronized correctly. And then to do the tape out, we just choose the pre-check job and start it in the same way that we did before. And this takes a lot longer. We'll be waiting for about an hour for this to go through. And now we've got a success. You can see it took about an hour. We've got the logs of the tape-out job as well. And at this point, your design is ready to be committed and submitted onto the shuttle. So I hope that walkthrough helps you see the whole process and helps you make a submission so you can take the most of this great opportunity that we have to get your ASIC designs made absolutely free by Google. So thanks very much to Google and Efabless. Good luck and get in touch on the Slack if you have any problems or you need any help.